Kotwal, and I welcome you all on the next lecture of course Fluid Mechanics with course code ME404. So in last class, we have studied about boundary layer theory. We have seen the various definitions like laminar boundary layer, turbulent boundary layer, and laminar sublayer. So let us move with the next topic, that is boundary layer thickness. So what is boundary layer thickness? It is defined as the distance from the boundary. If a solid body is kept in a flowing fluid, that solid body is represented by AB, then it is defined, boundary layer thickness is defined as the distance from the boundary. With this distance from this plate of the solid boundary measured in y direction. Y direction means perpendicular to the AB, to the point where the velocity of the fluid is approximately equal to 0.99 times the free stream velocity u of the fluid. What does it mean? That boundary layer thickness is defined as the distance from the plate in y direction where the fluid velocity will attain again 99% of the actual velocity. As we have seen in boundary layer theory, that when we put a plate in a flowing fluid, there is a reduction in the velocity of this fluid near to the plate. So, and that reduction will be more to the plate to the layer which is near to the plate, and that reduction will reduce, means the velocity will increase when we move in the direction of y. So boundary layer thickness is the point, is the distance from the plate to the point where the velocity again reaches its 99% of the original velocity of the free stream velocity. Again, let us understand it in another way, that when we keep a plate in a flowing fluid, the fluid layer which is very much near to the boundary or solid boundary or plate, its velocity reduces to 0. And the velocity of layer which is just adjacent to the fluid is somewhat greater than 0. And when we move upward in the direction of y, the velocity will continuously increase. And a point will reach where the velocity will become 99% of the velocity of the actual free stream velocity. So that point is fixed, and the distance between that point and plate in y direction will give the boundary layer thickness. Okay, so it is denoted by the symbol d. Now this boundary layer thickness is of three types. First one is displacement thickness. So displacement thickness is defined as the distance measured perpendicular to the boundary of solid body by which boundary should be displaced to compensate for the reduction in flow rate on account of boundary layer formation. See what is happening when we keep a solid plate in a flowing fluid, the velocity of the fluid will reduce, and because of this reduction in velocity, flow rate will reduce. So we can say that by keeping the solid plate in a flowing fluid, the flow rate of the fluid is decreasing. So displacement thickness is the distance by which we have to move this plate in order to compensate the reduction in flow rate which is occurring because of the presence of this plate. So there is a derivation related to this, and let us see the derivation. So we have taken a plate, and the velocity at point B is 0, okay, and at C, which is at a distance delta, suppose, is u. So the velocity varies from B to C, from 0 to capital U. And in this BC, we have taken section 1,1. We have given the name is as section 1,1, and this distance BC is delta because delta is our boundary layer thickness. Okay, now with the help of this delta, we are going to calculate the displacement thickness. So at section 1,1, we have taken a strip. Okay, in that strip, we have considered that the velocity of fluid passing through this strip is u, and the width of this strip, means which is not being seen to us, it is perpendicular to the screen of the computer. So that width is b, and the velocity which is passing through this section, a small strip, is u, and the thickness of this strip is dy, and that strip is located at a distance y from point B. So this is the strip. Actually, I have shown this in this plane, but actual this profile is perpendicular to the screen of the system. So to understand it in a better way, I have to show it in this screen. So we have considered a strip of width b, this length is b, thickness is dy, located at a distance y from point B in perpendicular direction. So let's start then. Now the area of the strip will become dy thickness into width b, that is b into dy. So the mass of fluid passing through this strip will be density into velocity into area. Density we have taken rho, velocity we have assumed small u, and area is b into dy. So it will be rho u b into dy, give this equation 1. Okay. Now suppose if there is no plate, if the plate is not there, then what will happen? There will be no reduction in velocity. So if the strip will remain same, if we'll study about the same strip, then the velocity of fluid in this strip will be capital U if this plate is not present, because there will not be any reduction in velocity of the free stream velocity, and the reduction is taking place because of the presence of this plate. So let us assume that this plate is not present, then this strip, the velocity of fluid flowing with this strip will become obviously capital U. So it is written there. In that case, what will be the mass of fluid flowing per second? It will be rho, density will remain same fluid, velocity will change to capital U, and the area of strip will remain b into dy. Give this equation 2. So this is the mass flow rate with plate when the plate is present. This is the mass flow rate when the plate is not present. Now it is obvious that capital U is greater than small u. So the presence of plate, it is decreasing the mass flow rate of the fluid through this elemental strip. So what is the amount of reduction? That will be the mass flow rate without plate minus mass flow rate with plate. So it will be given by rho in bracket capital U by small u into b into dy. Okay. Now this is for this small strip. Now if we'll talk about the complete displacement from B to C, how much will be the reduction in flow rate? Then we have to mass rate, then we have to integrate it from B to C. So integrating this from 0 to delta, B to C means from 0 to delta, because here the boundary layer thickness is delta rho into B capital U minus U dy, and this density and width of strip is constant. Okay, so it will come out of the integration, gives this equation 3. Now let the plate is displaced by delta star. Now what we are doing, we are displacing this plate by delta star in order to compensate for the loss. So the velocity of flow for the distance delta star will be equal to the free stream velocity, and the loss of fluid per second flowing through the distance delta star will be rho into u into b into now delta star. Now see what we are doing. We are moving the plate by a distance delta star in y direction. When we move the plate we will move the plate by delta star distance, then what will happen? The velocity, mass flow rate of velocity will reduce, because now the plate is moved to a distance delta star, and because of that the fluid which is flowing past the solid body will reduce, and that reduction will be rho u, use the free stream velocity, the width of the plate is constant b, and now we have moved the plate by delta star, so it will be rho u into b into delta star. Give this equation 4. Now equating equation 3 and 4, because the loss will be same as that of the loss that is happening because of the plate, because we are doing displacement thicknesses, that only that in how much distance we have to displace the plate in order to compensate the loss that is occurring because of the presence of the plate. Okay, so that equating equation 3 and 4, what we will get equation 3 in left hand side and equation 4 in right hand side. Then we have to calculate delta star, so we have to keep delta star on one side and rest of the thing on the other side. Now this is the formula for displacement thickness that we have used in, that we are going to use in numerical, where u if we'll solve it further, we'll get delta star is equal to integration 0 to delta in bracket 1 minus small u by capital U into dy. Okay, so this is the delta star, that is displacement thickness. In numerical, what will be given? The velocity profile u by u will be given, and we have to calculate this delta star from that velocity distribution curve. Now let us move to the momentum thickness. Similar to the displacement thickness, again because of the presence of fluid in displacement thickness, flow rate is decreasing, here again velocity is decreasing, so momentum will also decrease. So the momentum thickness will be defined as the distance measured perpendicular to the boundary of the solid body by which boundary should be displaced to compensate for the reduction of momentum of the fluid on account of boundary layer formation. So in this case, we have to displace this plate in such a way that the reduction occurring in the momentum of the fluid because of the presence of plate will be compensated. So again, there we have calculated mass flow rate. Here we have to calculate momentum, that is mass into velocity. So mass flow rate through this strip is already taken as rho into u into b into dy. Now momentum, we have to convert this in momentum, so we have to multiply it by u. So mass into velocity will give momentum. So momentum of fluid passing through this strip will be rho u b dy into u. Similarly, in the absence of plate, what will be the momentum of the fluid passing through this strip? This small u will be replaced by capital U, because if the plate is not present, the velocity of fluid through this strip will become capital U. So what will be the loss of momentum? Loss of momentum will be higher momentum minus lower momentum. Here capital U is greater than a small u. So this momentum will be high and this momentum will be low. So this will be the loss of momentum. Taking the loss through BC, we get 0 to delta. This loss of momentum is for this small strip. So for complete length delta over the complete thickness delta, what will be the loss? Integration from 0 to delta, we have to integrate this and we have to give this equation 1. So this is the total loss of momentum through the displacement thickness BC, that is delta. Okay. Now we have moved this place by delta in order to compensate the loss. So then what will happen? Then the velocity of the flowing fluid will be constant, that is u, and loss of momentum of fluid through distance delta with velocity u will be given by mass of fluid flowing through delta distance into velocity. Mass of fluid flowing through delta distance will be area into density into velocity. Now density will remain same, rho. Area, velocity will remain same, u, and area will be b into theta, because theta is the distance, b is the width. So in earlier case, in place of displacement, we have multiplied this b with delta star. In this case, we have to multiply this b with theta, because in this case we are moving our plate through a theta distance. So and multiplied by velocity, so we'll get rho b theta into u square, give this equation 2. Now again we have to equate equation 1 and equation 2. What we'll get? We'll get this equation 2 in left hand side, equation 1 in right hand side. Putting theta in left hand side, rest of the thing move to right hand side, can reduce our equation as theta is equal to 0 to delta u by u 1 minus u by u into dy. So this is the formula for momentum thickness. Now last, energy thickness. Similarly, again following the same thing, if the velocity is decreasing because of the presence of this plate, we have seen that flow rate will have decreased. We have seen that momentum had decreased. So again, the kinetic energy will also decrease. So here we have to take that kinetic energy into account, and with this energy thickness is defined as the distance measured perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for the reduction of kinetic energy of the flowing. So here we have to move this boundary in such a way that the loss occurring because of the presence of plate in terms of kinetic energy will be compensated. So again, we have what we have to do. We have to calculate the mass of fluid flowing through this strip. Then we have to convert this into kinetic energy by multiplying mass into velocity square. Let us see, kinetic energy of the fluid will be half mv square, half mass of the fluid flowing through this strip into velocity square. Mass will, we know, rho into b into dy into small u will be the mass, rho b dy into u. This will be the mass flow rate through this strip. And when we multiplied it by velocity square, the velocity of fluid passing through this strip will get kinetic energy of the fluid. Now suppose when the plate is not present, what will be the kinetic energy? This small u will be replaced by capital U. So in absence of boundary layer, the kinetic energy will be half rho, this is capital U, this by u square. Okay. So loss of kinetic energy will be half, no, this will be small u only. So half rho into u into b dy into capital U square minus small u square. This will be the loss of kinetic energy. Now again, same thing, total loss of kinetic energy will be integration from 0 to delta half rho ub capital U square minus small u into dy. This loss is through the strip only. So to calculate the complete loss, we have to integrate this from 0 to delta. So total loss in kinetic energy will be integration from 0 to delta 1 by rho ub capital U square minus small u into dy. Now again we have to equate this with what? We have to move this plate by delta double star to compensate for the loss of kinetic energy. So in that case, what will be the kinetic energy? In that case, kinetic energy will be half rho u b into delta star. Again, area will change only, b into delta star in first case, b into delta star in for displacement. For momentum, b into theta. Here, b into delta double star, because delta double star we are considering our energy thickness, and this will be u square. So it will come 1 by rho b delta star into u cube equation 2. Again, what we have to do? We have to equate equation 1 and 2. While we equating equation 1 and 2 and keeping delta double star on the one side, what we will get? We will get 0 to delta small u by capital U in bracket 1 minus u square by u square into dy. So with this formula, we can calculate the energy thickness. So in this way, we can calculate three different boundary layer thickness, that is displacement thickness, momentum thickness, and energy thickness. More chances are that in exam that numerical will be asked, but this derivation is also important. So we have to understand this derivation. Thank you. In next class, we will study about von Karman momentum integral equation. Thank you very much.